Good afternoon, everyone. I am Ankit Jha, and here I am. I am excited to talk with you today about a fundamental and often underappreciated algorithm in computer science, insertion sort. Now, if you have taken my any intro to algorithm course, chances are you have come across it. But what we will do today is go beyond just the code. We look at where insertion sort shines, where it struggles, and why, despite being a basic algorithm, it's still useful in modern computing. So let's jump into how this algorithm works and why it matters. So here's what we will cover. First, I will define insertion sort and its purpose, what problem it solves and how. Then we will walk step by step through how the algorithm actually works. After that, we will do a deep dive into its performance, both in terms of time and space complexity, and what that means in practice. Finally, we will wrap up with conclusions and discuss the real-world cases when insertion sort might actually be the best tool for the job. The goal here is not just to know how it works, but when to use it and why. The following slides I will talk about the insertion sort's definition and purpose, its key characteristic, and its time complexity and the space complexity which it has, and how and which are the best cases it will work and which are the worst cases it will work for. Insertion sort is a simple and intuitive sorting algorithm that builds a sorted array one element at a time. It's particularly efficient for small datasets or partially sorted arrays. Its primary purpose is to reorder a sequence of elements into a specific or specified order, typically descending or descending. So I will break down what's written here. Let's start with the basics. Insertion sort is a simple and intuitive sorting algorithm. You can think of it like sorting a hand of playing cards. You pick one card at a time and insert it into right place in your hand. That's literally what this algorithm does. It builds a sorted array on one element at a time. What makes it different from something like merge sort or quicksort is that it doesn't divide and conquer or recurse. It just builds up a sorted section by comparing and inserting each new element. And while that might not sound high tech, it has some very real advantages, especially in environments where speed isn't the only factor. Like when code simplicity, memory use, or predictability matter. Its primary use is to reorder a list of elements, usually numbers, in ascending or descending order. That may sound basic, but sorting behind everything from search optimization to machine learning for preprocessing. Insertion sort functions by iteratively taking one element from the input data and placing it in the correct position within the sorted portion of the array. Initially, the first element is considered sorted. Subsequent elements are compared with the sorted elements and the proper placement is identified by shifting larger elements to the right. The process continues until all elements are sorted. Now, let me walk through the logic of algorithm. Imagine we have an array of numbers. We treat the first element as already sorted. Then we pick the second element and compare it to the sorted portion. If it's smaller, we move the first element over and insert this one before it. We keep doing this, picking one element, comparing it to the left part, shifting bigger elements to the right, and inserting the one new one into the correct position. So after every step, the left side of the array is fully sorted and the right side is unsorted. It's worth noting that it's not just simple, it's also easy to implement and doesn't require extra memory or recursion. But of course, the simplicity comes with trade-offs, and we will talk about this in a bit. Insertion sort is characterized by its simplicity and effectiveness on small data sets. It's an in-place sorting algorithm, meaning it requires minimal additional approach for execution. It has a stable sorting nature, maintaining the relative order of equal elements. This algorithm works well with nearly sorted data, leading to reduced operational time in such scenarios. Let's talk about what makes insertion sort stand out. First, it's an in-place algorithm. That means it doesn't require additional memory beyond the original array, just a few variables. So it's efficient in low memory environments. Second, it's a stable algorithm. That's important in cases where elements might be equal but we want to preserve their original order, like when sorting names alphabetically while keeping them grouped by company. Third, and this is key, insertion sort is adaptive. It performs particularly well on nearly sorted data. So while it might be slower in general on or small on partially sorted datasets, it can outperform more complex algorithms like the quicksort or merge sort. It's also very unpredictable. It doesn't have sudden spikes in memory or time use, which is important for embedded systems or real-time environments. Now, as you all know that insertion sort basically is a decrease and concur sorting technique. So now we will analyze the algorithm based on its time and space. Time time complexity basically the total time computed in used in computing the algorithm, and space complexity total space required to use to compute the algorithm. Okay, now let's dive into performance. The time complexity of insertion sort depends entirely on the input. In the worst case, say when the input array is completely reversed, every new element that has to be compared with everything before it and moved to the beginning. That's big O of n squared time. But in the best case, where the array is already sorted, each element only needs one comparison. That's big O of n time. The average case for randomly ordered data is also around big O of n square. So yes, it can be efficient for large unsorted data sets. But here's the thing. If your data is already 90% sorted, and that happens more often than you would think, insertion sort can be incredibly fast. That's why some modern hybrid algorithm like time sort used in Python actually use insertion sort for small data checks. This efficiency makes it suitable for smaller lists where the overhead of more complex algorithm does not yield a significant performance gain. Let's move to memory usage. The insertion sort has a space complexity of big O of 1. It sorts the list in place. That makes it incredibly space efficient. There is no recursion, no extra arrays, no stack overflows. This is one of the reasons it's still used in embedded systems and microcontrollers. When memory is tight, it's also why it's often used in combination with other sorting methods, acting as a helper that cleans up small or partially sorted piece of data. This makes it an efficient choice in environments with limited memory resources. Let's look at the two extremes to really understand how performance varies. Basically, the best and worst and the average case scenarios I will tell here. In the best case scenario, which occurs when the input or array is already sorted, insertion sort runs in big O of n time. In the best case scenario, the fully sorted array, insertion sort makes n minus 1 comparisons and 0 shifts. That's the dream case, and it happens more often than you might expect in real applications. Now I will talk about the worst case. When the array is reversed, each new element has to be compared and shifted all the way to the front. This leads to the n squared by 2 operations, which is much slower. This shows just how much the algorithm depends on the initial order of the data. Again, it's it's why we call it adaptive. Its performance improves the more sorted your data already is. So it's the fastest general purpose sort, not the fastest general purpose sort. It's often the most efficient in specific cases. To summarize, insertion sort is simple, stable, adaptive, and memory efficient. It may not be the algorithm you reach for when sorting millions of items, but in the right context, such as small lists, nearly sorted data, or memory constrained environments, it's a powerful tool. Understanding this algorithm gives you a better case of how sorting works in general and helps you make better decisions when choosing which algorithm to use. And hey, if you ever stuck in a coding interview and need to write a sort by hand, insertion sort might just save the day. This is basically my conclusion on how the insertion sort works. And thank you. That brings us to the end of the presentation. Thank you so much for your time and attention. I hope you have a deeper understanding of how insertion sort works and where it fits in the algorithm toolbox.